Hello, this is Anna Doblas from UMass Dartmouth, and in this video we're gonna solve 4 problems of the multi-choice questions of module number 3 that is about Gaussian optics. The first question is about you are given a Gaussian beam and you know the wavelength. So the wavelength is 500 nanometers and you know that the beam weight is 2 millimeters. And they are asking you what you need to solve is the Rayleigh range. So if you remember on the notes of the class, we know that the Rayleigh range is pi and then the square of the beam weight over lambda. So this problem is pretty straightforward since we already know the beam weight. Remember, this is the beam weight. And now we know the wavelength of the source, 500 nanometers. So I'm writing everything on the meters. So when you plug the numbers, that is going to be 25.1327. So if you cannot look the problems, the correct answer is going to be B. And this is how we solve the first one. On the third problem, on the sixth problem, they told us that you have a green laser, and they already told you that the wavelength of the green laser is 532 nanometers. And emits a Gaussian beam where you know the beam weight is 160 microns. And they know that the beam weight has increased to 2. So you know that in some moment, in some distance C, now you have moved from 160 microns to 1 millimeter. And the problem asks you how far you are. So you know that the beam weight, kind of like this is the minimum value, this is the beam weight, and now you are kind of measuring here when you have 1 millimeter, and they want us to estimate the distance C. So if you go to the equation of the beam width, you know that you can write it down as the beam weight multiplied by the square root of 1 plus C over the Rayleigh range square. So we can move the beam weight to the left side of the equation. So we have the square root of 1 plus C over C0 square, and then we have the square root of C over the square, not the square root, the square of the beam width over the square of the beam weight, 1 plus C over C sub 0 square. So this is at the end, like C is gonna be equal to the Rayleigh range, and now the beam width square over the beam weight minus 1, and all of that square root. So if you remember the first problem, we can write the Rayleigh range in terms of the beam weight because we don't know the Rayleigh range. So we put here pi, the beam weight over lambda, it's equal to the square root of the beam width over the square, the square of the beam width over the square of the beam weight minus 1. And now here we have everything. We know the wavelength, and again I'm putting everything on the meter. We know the beam, we know the beam width, so that's gonna be 1 minus 3 meter, and now we know the Rayleigh range, 160, then minus 6 meter because it's in microns, so at the end this is gonna be 0.9327 meters. So 93.27 centimeter. So the solution is gonna be A. Now, problem number 10. It tells us like we have a Gaussian beam, and we know that the beam weighs is 797.88 nanometers, and we know that the radius at the distance of 4 microns is 10.25 microns, and we need to estimate the wavelength, the color of the beam. So we're gonna start with the radius of curvature formula, that is telling us that C1 plus C sub 0 square over C square. So remember, this is gonna be the Rayleigh range. So the radius of the curvature over the distance minus 1, this is gonna be the square of the Rayleigh range over the square of C square. So I can move the C on the other side, so I'm gonna have, and then we make the square root. So the Rayleigh range is equal to C square root of the curvature over C minus 1. And now we need to remember that the Rayleigh range is pi the beam weight square over lambda. So I can write here pi the square of the beam weight over lambda equal C the square root of the radius of the curvature over the distance minus 1, and we want to estimate lambda, so lambda is gonna be equal to pi beam weight square C over the radius of the curvature divided C minus 1. And again, now we have everything here. Now we know that the beam weight is 797.88 10 minus 9 meters. The radius is gonna be 10.25 10 minus 6 meters, and then C is gonna be 4 10 minus 6 meters. So that's gonna be 4 10 minus 7 meters, so that is like 410 minus 9 meters, so that is 400 nanometers. So the correct answer is gonna be B. Finally, the last problem that we're gonna go, it's about doing propagation of a Gaussian beam using ABC matrix. So they told us here that we have a Gaussian beam that propagates at distance f, meets a length, and then it propagates again. So we have here a Gaussian beam. What you have here is you have free propagation. So you have 1 f(0)(1). So remember, this is free propagation. Then emit a length, and if we don't know anything about the length, we're gonna assume that it's a converging length. So this is gonna be our length. And now it propagates again. So we have 1 f(0)(1). And here we have another beam where here we have our Q1, and this is gonna be our Q2, right? So we know that if this is my input, whatever system I have, and this is gonna be my output, the new Q value is gonna be A Q1 plus B divided C Q1 plus D. So we need to find the ABCD matrix of the system. And remember, the system is gonna be, now when we write the system, we're gonna write it in a reverse way. So we're gonna go from the right to the left. So we're gonna have first 1F01. So this is gonna be my second propagation, and now we're gonna have our length. It should not make any difference here because the system is completely symmetric. And then we have another propagation. And now if you cannot write, this is gonna be 1F01. Now the product of the other two is gonna be 1F minus 1 over F0. So we have here 0F minus 1 over F0. And this is gonna be the ABCD matrix of the system. So now we know that A and D are equal to 0. B is F. And C is minus 1 over F. So Q2 is gonna be B. So B is gonna be F. And then on the bottom, we're gonna have minus 1 over F Q1. So that's gonna be minus F squared over Q1. So that's the solution. And if you see, this is gonna be the C answer. So I hope that those videos help you a little more about Gaussian beams. If you have questions, please shoot me an email. Thank you.